Okay, so this is Nuclear Lesson 3, and today we're going to focus on half-life, the amount of time it takes for 1/2 of a sample to decay. And we're going to use Table N. And we're going to look at a variety of half-life problems and how you should be thinking, your mindset, when you solve these problems. So radioactive decay is a random process. It's not possible to predict when a particular nucleus will decay, but we can make some fairly accurate predictions about how many nuclei in a large sample will decay in a given period of time if we know some certain information about that sample. So if a sample contains 1,000 nuclei of a radioactive isotope, now 500 will undergo decay over the course of one half-life, because one half-life is, as I said, the amount of time it takes for 1/2 of the sample to decay. Another example, if a sample contains 4 grams of a radioactive isotope now, after one half-life, 2 grams will remain undecayed, and the other 2 grams will have made up a more stable isotope. We can use a Geiger counter to count the time period of what the half-life will be. Another way to look at it is sometimes a problem will say after one half-life, 50% of the original amount of sample will have undergone radioactive decay. After a second half-life, 1/4 or 25%. So we can look at this as, let's say I had 100 grams of a sample. After one half-life, 50 grams are left. After another half-life, 25 grams are left. And after another half-life, 12.5 grams are left. Each of these arrows represents a half-life. So here you can see after 3 half-lives, 12.5 grams of a sample would be remaining. Some general steps to follow when solving half-life problems are, number 1, if you know how much of the isotope you have now, you want to find out how much will be left after a certain amount of time in the future. That could be one type of problem. In this case, you would have to determine how many half-lives have gone by. So, you know the starting mass, and you know one half-life. If you take the total amount of time that's elapsed and divide it by the half-life, that will tell you how many half-lives that went by, and then you can just cut your sample in half so many times and figure out what the ending mass is. Let's look at an actual problem. So here it tells you the half-life of Rn-222, which is a carcinogenic house pollutant, is 3.8 days. So I'm just going to write that down over here. I'm going to write half-life equals 3.8 days. If today your basement contains 20 grams of Rn-222, how much will remain after 19 days, assuming no more leaks in? So my sample size is 20 grams, and my total time, so we can call this time elapsed, equals 19 days. So what I want to do is I want to take my total time, 19 days, and divide it by my half-life, 3.8 days, right? And that's going to give me approximately 5 half-lives. So now what I'm going to do is I'm going to take my sample of 20 grams. Half of 20 is 10. Half of 10 is 5. Half of 5 is 2.5. Half of 2.5 is 1.25. And half of 1.25 is 0.625 grams. And I underwent 1, 2, 3, 4, 5 half-lives. And I wound up with 0.625 grams, which is exactly what they show you over here on the bottom. All right, let's do a couple more examples. It says a laboratory sample of P32 triggers 400 clicks per minute in a Geiger counter. How many days will it take for the P32 to decay enough so that there are only 50 clicks per minute? So first we have to figure out how many half-lives took place. We know the starting is 400. Half of 400 is 200. Half of 200 is 100. Half of 100 is 50. So if I count my half-lives, I've got 1, 2, 3. It underwent 3 half-lives. Now, if we go to table N and we look up the half-life of P32, it tells us P32 has a half-life of 14.3 days. So they want to know what's the total time. So if we take 14.3, which is 1 half-life, and we multiply it by 3, we will have our total time. So it's a total of 42.9 days to cut 400 counts per minute down to 50 counts per minute. All right, let's look at the next one. A cylinder contains 5 liters of pure radioactive Ne-19. If the cylinder is left to sit for 103.2 seconds, what percent of our original sample of Ne-19 will remain? Well, the first thing we need is the half-life of Ne-19. We go to table N, and you see that that is 17.2 seconds. So remember, the number of half-lives equals the total time. We know our total time is 103 seconds, 0.2 seconds, divided by the half-life of 17.2 seconds, and that's going to give us our half-lives, which is going to equal, we need it to be a whole number, okay, 6 half-lives. Now we're not done. They want to know what percent will remain. So if I start with 100%, $50, $25, 12.5, 6.25. Let's see how many half-lives I'm up to. 1, 2, 3, 4. I need 2 more half-lives. Half of 6.25 is 3.125, and then I need 1 more. Half of 3.125 is 1.56 and change percent. So there is my 5th half-life and my 6th half-life. And then I have my answer. All right, in the last problem, the half-life of TC99. It's used to, that's Tectenium-99 is used to locate brain tumors. So the half-life is 6 hours. If 10 milligrams are left after 24 hours, how much TC99 was administered. So first thing that I can see when I look at this problem right off the bat is I know the half-life. 6 hours, I know my total time. So you know right away I'm going to divide 24 by 6, and I'm going to get 4 half-lives. It underwent 4 half-lives. Okay? So it says I was left with 10. So what I like to do is I work it backwards. So I know my ending mass. So I would start and go from 10 to 20, 20 to 40, 40 to 60. Sorry, 10 to 80, and 80 to 160. So 160 was the original sample. Okay, a laboratory sample of P32 triggers 100 clicks per minute. How many days ago did the P32 decay enough to produce 1,600 clicks per minute? So we need to find out how many half-lives took place. We went from 100 to 1,600. So I've got 1,600, 800, 400, 200, 100. So I underwent 1, 2, 3, 4 half-lives. So I need to know the half-life of P32, which is 14.3 days. So we looked this up before, right? P32 equals 14.3 days. And it underwent 4 half-lives. So 14.3 times 4. So I get a total of 57.2 days. So in another type of problem, you may want to find out how long the half-life is, knowing how much a sample has decayed over a given amount of time. So in this type of problem, you have to determine how many half-lives you can cut your original amount in to get your final amount. That will give you the total number of half-lives that have gone by. Then if you divide the total time that has elapsed by the number of half-lives, then you can find out the exact time of one half-life. So let's look at an example. A radioactive sample is placed next to a Geiger counter and monitored. In 20 hours, the Geiger counter's reading goes from 500 counts per minute to 125 counts per minute. How long is the half-life? So the first thing that we want to do is figure out how many half-lives took place. We know that we started at 500. Half of 500 is 250. Half of 250 is 125. So I got my starting and ending mass there, and I know that 2 half-lives took place. I also know that it was a total of 20 hours. So 20 hours divided by 2 half-lives equals 10 hours. And that equals 1 half-life. Easy enough. And in this last problem, a sample of pure radioactive isotope is left to decay. After 40 days, the sample is placed in a mass spectrometer, and it is determined that the sample only has 25% of the original remaining. How long is the half-life? Well, we can always assume that a sample starts with 100%. So after one half-life, 50% is left. After another half-life, the second half-life, 25%. So I got to my 25%, and that was 2 half-lives. So we know that it was a total of 40 days. So 40 days underwent 2 half-lives. That means that each half-life is 10 days. All right, one more slide left. So in this type of problem, we can use radioactive dating to determine the age of a substance, how old it is, that contains a radioactive isotope of known half-life. So determine how many times you can cut your original amount in half in order to get to your final amount. So we're going to start with our starting mass, our ending mass, figure out the total number of half-lives. And then we just multiply the number of half-lives by the duration of one half-life. We did this earlier, and that will give us our total time. So in this example, the oldest rocks on Earth have been found to contain 50% U-238, 50% lead-206. What U-238 ultimately decays into? So we want to know what the age of these rocks are. So as the U-238 decays and decays and decays, it eventually will become stable at lead-206. So first we need to find out how many half-lives have gone by. So to go from 100 to 50 is only one half-life. And then if we look up U-238 in table N, it is 4.51 times 10 to the 9th years. So it only underwent one half-life, so that's how old it is. If it was more than one half-life, we would multiply it by the 4.51 times 10 to the 9 years. An ancient scroll is discovered, and it's found that only 25% of the original concentration of C14, which is a radioactive isotope, remains. How old is the scroll? So, again, assuming everything's 100%, 50%, 25%. So this underwent two half-lives, 1, 2. I go and look up carbon-14 in table N, and I see that the half-life is 5,730 years. But it underwent two half-lives, so I have to times that by 2. And that is 11,460 years total for the age of a sample. Some uses of radioactive isotopes that have been asked on Regents exams in the past are listed as follows here. I'm just going to highlight the most important ones. Carbon-14, you need to know that one. I-131. Cancer is usually pretty important. And then the only other one that I usually see is the U-238, the last one, the age of rocks. Okay, that's it. Go try the homework and then check your answers on Schoology.